All right, when I had to decide on a title, I thought of saying irrigation management, why bother? Because many of you have heard me so many times talking about this topic, but it remains a very important topic. And therefore, I'd like to share a few ideas with you. Potato, I would think you would agree with me, is a very highly productive crop and one of the most water-efficient food crops. And I'm sure you've seen of these numbers before, which is expressed as the liters of water required to produce each of those products. And for instance, if you look at orange, 50 liters to produce one orange, 70 liters to produce an apple, and so on. And of course, if you go to animal products, the numbers rise dramatically. And if food gets processed, the same applies. So if you look at the potato there, one of the lower water users, so very efficient in the use of water to produce food, at 25 liters to produce one potato. And from our local work, we've shown that we found that we are at around 19 liters to produce one medium-sized potato of 150 grams. So, and I think that's something that we have to sort of promote more, and so that the consumer and the man in the street know those facts. But in spite of the fact that potato is highly productive, very efficient, it is drought sensitive. Because of its shallow and poorly developed root system, and also the crop start to stress even at mild water shortages in the soil profile, compared to most of our grain crops. And therefore, in many parts of the world, and especially in our country, supplementary or full irrigation is necessary in order to produce economic yields. Of course, we know that our water resources are limited, and this is not going to improve soon. If we look at the water used by different sectors, and this is not up-to-date numbers, but it gives you a very good idea of what proportion of water is used by which sectors. And it is clear that irrigation by far utilizes most of the fresh water that we utilize in this country. If we look at the global risks forecasted for the year 2040, and where risk is expressed as the ratio of water extracted or withdrawn relative to the water supply, in other words, the water available. So the higher that ratio, the more water stressed. This is the situation for the world, and you can see South Africa fall in that red color there, and which is high water stress, which means that up to 80%, depending of course where in the country you are and what sectors they are, up to 80% of the water that is available will be utilized, leaving very little remaining in rivers. So that's a worrying situation. Since agriculture is the biggest user of water, we have a responsibility to manage our water resources as well as we can. And of course, you all know the consequences of poor water management, resulting in lower yield and quality, but also, of course, poor management can result in water losses and losses of nutrients because of over-irrigation. And of course, that leads to unsustainable production. That's not something that we would like to be known for. So, just having some of you may have seen this before. This was a study that we did a couple of years ago, where we looked at water use efficiency as part of a bigger survey in different production regions. And those are the numbers for those different colors represent different production regions. And you can see there's quite a variation. The average water use efficiency, 80 kilograms per hectare per millimeter. And but you can see there's a big range between different regions. And that can to some extent be explained by differences in climates, differences in soils, production conditions and so on. But still, the variation is quite high. What is a bit more disturbing is if you look at individual growers within the same region. And there's 12 different fields that that was surveyed, and you can see the average around 95, which is not bad, but you can see once again quite a big range in efficiencies, and often neighboring farms varying quite a lot. So what is the reason for that? And it mostly lies in irrigation management. The way that water is applied and how the farmer manages it and the different aspects covered by irrigation management. So we have to manage our irrigation efficiently, of course, to be more efficient, to produce more crop per drop. And there are various factors that play a role in the management that is covered actually by management. It's not only irrigation management, but it's also things like system type. Yachian spoke about drip irrigation just before me. Most of the work that we do focused on pivot irrigation because that's by far the biggest proportion is pivot irrigated. But I'm going to touch a bit on system type, irrigation system design, and especially maintenance, which is in the farmer's hands, and then irrigation management. And there are, of course, many other factors that also play a role, but I'm going to, because of limited time, focus on these three. I think we've all seen these tables of published material or literature on efficiency of systems, and you can see within each of those systems there's a huge range. But the general acceptance is that flat, or in this case furrow, is the most inefficient, but you can see it can go actually very high under certain conditions and certain management conditions. So the range that we see there often depends on the conditions and how that system is managed. If we look at center pivot, for instance, 70 to 95, in the work that we did in the last 10 years or so, we measured the efficiency of around about 80, 90 center pivots. And the average for those systems was 84%, which is not bad. But if you look at the range there, we found systems very, very efficient, depending on whether the system was properly designed and how that system is managed by the farmer. Of course, there are the few exceptions where the efficiencies are low because of various reasons, which I'll touch on now when we come to maintenance, but in general, efficiency of center pivots, if managed and designed well, can be very high. So the punchline here is select the most suitable system for our conditions. People often say that I'm against drip. I'm not against drip. I mean, we've done the first drip irrigation work ourselves in around 1996 in Limpopo, and Mosi is sitting here on his farm. And we found that it can work, but there are practical things that often limit the use of it under our conditions, which is probably the reason why it's not used so widely as in other places of the world. Okay, system design and maintenance. It is of critical importance that systems are properly designed by the engineers who sell it to you, or the company who sells it to you, their engineers, and the maintenance is very important. Things like correct nozzle size and the selection is important to prevent things like runoff and drift. We don't want to see this in our fields. So therefore the system must be well designed, and if you move that pivot to another position, you must make sure that it still functions properly. Optimum pressure, I'll show you a graph now where pressure was a problem and the effect thereof on delivery rate of the system. Use pressure gauges and regulators if you have uneven fields. And remember, those regulators don't last forever. they need to be replaced at some point. Otherwise, they're not going to perform as they should. Manage leakages and blockages, and perform regular efficiency audits. It can be as simple as putting out a couple of rain gauges. This is now a proper audit that we performed there in that figure where we put rain gauges every 5 meters. We measure many things like the flow rate of water into the system, the speed of the pivot, etc., to calculate the efficiencies. But it is important to at least do some sort of check every now and then on your system. This is an example of rain gauge readings, and that graph basically show individual rain gauge readings from the center of the pivot to the outer end of a pivot, and you can see it's clear that there's firstly big variation in readings, and secondly a big drop in application rate as you move from the inner to the outer end of the pivot. So most likely problems like worn nozzles, pressure regulators that do not function properly, and so on, or main line that's not properly designed. All of those can be factors that play a role here. Right, let's talk about irrigation scheduling, which is the last of the 3 points that I'm dealing with today. And it deals with the simple questions of when to switch on your irrigation, when to switch it off, when to irrigate, how much to irrigate. And of course it depends on how much water the crop requires on a daily basis, which is affected by many factors, including environmental factors, but also the stage of my crop, the type of soil that I'm farming on, and so on. So it's the duty of the farmer or the irrigator to make sure that the crop gets the water that it needs. And it sounds very simple, but it's a complex system, and I think we all know that. So it's not simply opening and closing the valve or starting and stopping the pump. We need to somehow make those decisions, and that's where irrigation scheduling comes in, and irrigation scheduling tools. So even if you're a well-experienced farmer, you have to from time to time check, you have to estimate what is the crop water requirements and how much should be applied. This is an example of a field that we monitored where, in this case, daily irrigation was applied, and those red bars are irrigation, the black line is the daily water requirement by the crop, and you can see for the biggest part of the growing season, the irrigation was managed very well, where the demand met actually the water use very well, and as a result, no water was wasted under the center pivot. This is an example of an extreme case where the irrigation very often exceeded the irrigation requirement by the crop, and as a result there was quite a bit of drainage measured in this field. And of course you want to be where the first graph is and not where this one is. And it is simple to say, well, we should not, it should be easy to make sure that you're not at this point, but if you don't use some tools, it is not always so easy. So there are various tools available for irrigation management. Most of them measure or estimate either the soil, the plant, or the atmosphere. The most common method in use, I would say on most farms, at least in this country, is soil measurements. And it can be as simple as using a soil auger or a spade, digging into the soil to check your moisture, and complicated systems like sensors or probes that are installed in the fields, and very often giving you continuous readings over the growing season, and then used to sort of manage the water, soil water content within a certain range. In this case, one would aim to be in the green area for the duration of the growing season. So that's basically the growing season over time. So that scheduling, so many different types of probes available, and in most cases working very well. The second approach is to use atmospheric methods, and the previous speaker also spoke a bit about crop factors in evaporation. So ET, water use, evapotranspiration, is a factor of function of the crop evaporative demand, ET0, which we use weather stations for, and then a crop factor, which depends on the growth stage. So if I look at my crop, of course, when the crop is small, the water use will be less, and similar to that graph, reach a maximum in the middle of the season and then drop again. And the crop factors follow that similar trend. So, and usually these are published figures in tables, or you can also estimate it from your crop canopy. Some of the latest work that we did, and that's now quite a big trend in the world, is to use remote sensing to estimate my crop coefficients. So in that case, if you measure regularly, if you have satellite images regularly, you have a dynamic crop coefficient. It changes as you measure, as your crop develops. Okay, so in that case, in this specific instance, we use, for instance, NDVI, and this is a typical NDVI image where the red part, the crop was already killed off, and the green part, the crop is still growing. And typically, NDVI gives us a good indication of the canopy cover of green material. And coincidentally, that matches very well, so that's NDVI over a growing season. It matches very well development of the crop and the crop canopy cover that we can measure. So if we have NDVI measurements regularly, we can then, in that formula, replace the KC from a table with a KC that we get from whatever satellite index we use. So that's sort of a dynamic method of estimating my crop coefficient and my crop water requirements on a daily basis. So we've tested this, found very good results in the field, and we're now at the point of making that final step of deciding how to take it now to a practical, usable form, for instance, in application or scheduling service or whatever, to make it useful to growers in the end. Okay, lastly, I want to touch on plant-based methods. So I said there were soil methods, atmospheric, and then lastly plant-based methods. And there the most well-known is canopy temperature measurements, where infrared thermometers, similar to the ones that we used in COVID to measure our own temperatures on the forehead. That's something that's been done 20, 30 years already, where temperatures are measured of a canopy, and that gives you an indication of if the crop is stressed or not. And that, and then different indices can be are developed that can be used to decide if I have to irrigate my crop or not. Nowadays, some of those sensors can also be installed on, for instance, my pivot. So as the pivot moves around, it takes measurements of the canopy temperature, and that can sort of automate the whole system. We can also, from remote sensing, measure canopy temperatures using specific instruments on the satellites, where infrared thermometers or different bands of the electromagnetic spectrum are used to estimate whether a crop is stressed or not, and those different colors gives an indication where crops are stressed or not. And then there are models linked to that quite often, like the seawall model is a good example, where directly from satellite images which are processed, crop water use on a daily basis can be calculated. So there are actually so many different options. And then the last one is maybe one that's not so used in practice on farm level already, but the technology is developing fast, and mostly at this stage for permanent crops like trees, where the sap flow in the stem of plants are measured with instruments, and the rate of sap flow gives an indication of the transpiration rate, and that can then be used also to make decisions on irrigation requirements or not. Okay, to conclude then, I think we are all well aware of the fact that our country is a water-scarce country, already under stress, and the situation is not going to become any better. I think in one of these research committee meetings, maybe 10 years ago, Finney was still a research manager. I said there, we must realize that the water that you have available today is the most water you will ever have. So it's not going to improve in future. It's going to just become tougher. So we must make sure that we use our water resources sustainably by applying good management practices. And that includes maintenance of system selection and irrigation scheduling. And there are today various practical scheduling tools available, depending on your preference, depending on what works well under your conditions, but there is no excuse not to use any tools nowadays. I think for us as scientists and people who make a business out of this, the challenge is always to try and make the tools as user-friendly and as accessible as possible to our growers. And hopefully that should contribute in the end to improve water use efficiency of the farming sector, so that we're not accused of wasting water, but using, although we're still the biggest water user, using the water efficiently and sustainably. Thank you very much.